Welcome everyone to our project on surveying solar panels in post-war Syria. As a Syrian who grew up during the war, I'm familiar with lone blackouts caused by the deteriorating public grid. As you can see in this satellite image of the before and during the war, uh, the reliability of the network got very bad. So people had to reach for ad hoc solutions, starting with gas-powered generators and car batteries, and more recently they started using solar energy panels. As you can see, they've been widely adopted. However, this decentralized system where each apartment has its own setup is very inefficient. And so now that the war is over, the hope is to be able to reintegrate this into the power grid. However, to do that, one of the main tasks is to estimate how much energy these solar panels produce altogether. And to do that, the main goal is to find the area. So we plan to develop a deep learning workflow that allows us to segment the images from aerial drone pictures similar to this one, and so reduce the problem to counting pixels. However, there's a lot of irregular setup of these panels, and as you can see, their directions aren't perfectly aligned, and this can cause inefficiencies. So as an extra goal, we plan to find the angle for a solar panel assembly. So our first task, which was the biggest hurdle, is to procure our own data set. And we worked with local photographers to get drone pictures similar to this one, and we created custom annotating tools that match our needs, as you can see in the lower picture. However, we faced several difficulties. The first of which is that the roofs in Syria, the urban architecture in Syria is very different than that in the West. Roofs tend to be flat and very dense with objects. And also there are water heaters, solar water heaters that are very popular, and they're not what we desire. And these look very similar to the photovoltaic panels, as you can see here. And finally, due to logistical issues, there's a very limited amount of data, making it harder to get security clearances. And the drones that are available are all consumer grade, so the pictures, they can fly at lower altitudes and with low resolution cameras. And moreover, in wind conditions, as you can see, the angle is not straight down, which makes it impossible to use these pictures for estimating the angle of the installation. However, we came up with a solution, which is instead of looking for the angles, we reframed the problem as finding the corners of the solar panel assemblies. This allows us to use all of our data, therefore doubling the amount of useful data. And this allows us to produce 1,500 image patches from 9 source images for training and validation, and 109 test image patches from a single source image from a separate geographic area. And Nick will go over some of the technical details.
All right, thanks, Bra. So our model uses 3 stages. First, faster RCNN produces a bounding box around the panel. Next, SlimSam segments the box to produce a mask that estimates the area of the panel. Finally, our corner model, using the same backbone as our bounding box model, estimates the corners. We train specific model heads to predict the bounding box and detect corners before fine-tuning the shared model backbone between both of our models. We employed an active learning approach in this project, in which we iteratively updated the training dataset. Starting with a set of 300 labeled images, we train 32 model variants of our bounding box model, compute the classification entropy for each bounding box and for each model, and then find the average for each image over all bounding boxes and all models per image. Then we hand annotate the top 100 images for that cycle. Finally, we append the annotated images to the training dataset, and we repeated this cycle 3 times for a total of 700 annotated training and validation images. Now, Suman is going to talk about our results and future work.
Thank you, Nick. The table shown here compares the performance of our bounding box model against a baseline, which is a non-fine-tuned faster RCNN. The table also shows the metrics from other solar panel models in the literature. And although our image context is more complex, our model still achieves better result on our dataset. We have also built an app that lets users select models and run inference on chosen images. So for future improvement, we can acquire higher quality orthographic drone images to reduce noisy data during training, and also explore transformer-based architectures such as SolarFormer for potential performance gain. And lastly, we can develop smaller, efficient models, which is key for scaling in resource-limited environments. Thank you.